Okay, I wasn't quite sure what I should talk about today, but I'm going to weave in and out the big research project that I do that people know about and where AI is making its mark in what we do. But I'd like to, along the way, reflect a little bit on AI in physics and the fact that maybe in some ways, physics is a place where it hasn't made the kind of impact that you might think it would. If we look back at the last century and look at the advancement of technology, so much of it has started with physics of the most fundamental kind. The invention of the laser started with a concept of Einstein's. The MRI machine started out with another concept from nuclear physics that then both of those won Nobel Prizes, and later, people learned that it had applications. AI has made a much slower entry into physics. We use it all over the place, but I don't think in really the ways that is pushing the science forward. And I'll explain why I think that's true and what the problem is. Not a problem, what the limitation is. We started physics as a real subject in the days of Newton. And Newton taught us the scientific method as a way to determine whether what we do in our laboratories or in our heads and develop is true or not true by testing it against a set of criteria. And about in the 20th century, that got replaced. We still use a scientific method, but it's no longer Newton's steps. Instead, the predominant tool that we use to determine whether something that we do scientifically is true, whether it's a breakthrough in science or whether it's what we're going to build for a scientific device and trying to determine it quantitatively, is statistics. And it's statistical significance that we use to measure whether something's a true event. And the real limitation for us in applying AI traditionally or machine learning to physics has been the fact that it's basically allergic to each other. The statistical methods are the fact that we use neural networks, and for example, there is a black box that comes out. We can't tell what the statistical significance is. So if you look at the discovery of the Higgs boson, I know all the background work that's done, and we look at all the internal notes and know how much modern techniques like this were used in determining whether it was right or not. But in presenting it to our colleagues, if you look at the discovery of the Higgs boson, traditional statistical techniques are used to show that it's 5 sigma. And so the problem is that I remember the day that Max Delbruck came to Caltech, and he was brought by Murph Goldberger, our president at that time, who had come earlier from Princeton, and brought him to the physics department. And we tried to, I tried as a young faculty member to work with him to tell particle identification, whether you see a pion or a kaon or an electron or a photon in a detector, which again, by neural networks or nested neural networks, whatever you use, doesn't give you any probability, so that basically we've always done it by statistical techniques. And so it's been the limitation and still is today, and that's why I bring it up, in what role AI plays in physics. Now it's starting to play a big role in an everyday way, which I'll point out kind of in our experiment, but it's not as fundamental as it might be because of the fact that it's not related to statistical techniques in today's versions. And so that's the limitation with, or the bottom line of what I'll do. So this is the discovery of gravitational waves, the picture from the physical review letter that we wrote now 20 years ago, and 10 years ago, I'm sorry. And what it is the merger of two black holes. The scale from left to right is 0.2 of a second. And the scaled and the vertical one is the one that should be impressive. It's a number with a lot of zeros, 10 to the minus 21. And so we were able to make an instrument that could make a measurement to some small part of an effect that was at the level of 1 part in 10 to the 21. And that was the instrument without going through it in much detail. The reason there's 2 graphs is that in order for confidence and for other reasons, we built 2 different detectors. Part of the reason is to use 2 or then 3 to point to where something is in the sky. And the scale from left to right is the merger. As they get closer and closer together, it's a bigger and bigger signal, and then they merge together. So the traditional technique that we use to find this is what we call template banks. We go and calculate, using Einstein's equations, every configuration that's kinematically possible between 2 black holes or a black hole and neutron star, and we make roughly 250,000 templates that cover the parameter space that our instrument's able to cover. And then we compare the calculated template with the data 250,000 times on every piece of data. And that's basically where the events are discovered. In AI, we now use AI, but in what I'm calling a secondary way. We use convolutional neural networks trained on a simulated waveforms, and it enables us to do this more quickly. So that's not, to me, the revolutionary step forward, but by more quickly does enable us, in terms of gravitational waves, to make a quicker decision to tell astronomers whether we've seen something where they might turn their instruments and look at what we're seeing. So speed turns out to be important. Speed is something that we can get help from, and that's one aspect where we now are using these techniques. And this real-time ID quickly then, low latency, enables us to begin what people like to call multi-messenger astronomy. That is, that we see the same phenomenon in space and look at it in electromagnetic waves of all kinds, possibly neutrinos, and gravitational waves. So that's the goal, and that's why we do it quickly. This is LIGO itself. It's a very large instrument, even though it's so precise. The arms are 4 kilometers long, and there's 2 of them. One in Hanford, Washington, and one in Livingston, Louisiana. And there's a third partner, which is near Pisa in Italy, with a little different technical design, but that doesn't matter for today. We proposed this in the early 1990s to the National Science Foundation. They agreed to do it. The politicians, when they agreed to fund it, took our proposal to use a site near the Owens Valley, not so far from Caltech, and one in southern Maine, and they rotated for political reasons, but they funded it. So the job then is to actually compare and measure an effect that's 1 part in 10 to the 21, which translates in terms of kilometer size device to 1 part, a few parts in 10 to the minus 18 meters. And to do that, just to summarize what the biggest challenges are, is that we have to do interferometry, something that people here probably have seen, many of you in a laboratory in undergraduate school somewhere. We have to do it where you compare the 2 arms, light going down and coming back, to 1 part in 10 to the 12th of the wavelength of the light. And that's 7 or 8 orders of magnitude better than people had ever done with an interferometer. So there's many, many tricks I'm not going to talk about. The second thing that we have to do is, even though LIGO is on the Earth's surface, the main problem is the Earth. The Earth shakes. It's not that solid. And we have to basically float it or isolate it from the Earth again, getting rid of the Earth's vibrations to 1 part in 10 to the 12th. And those were the two major, if I summarize it, the two major problems that took us so many years to solve or get good enough that we could make the detection. So we made the first detection. If you just look, it was a merger of two black holes, which you can see in the table on the left, one 36 times the mass of our sun, another one 29 times the mass of our sun. That adds up to 65. And you'll notice that the final mass that we also measure is 62, which means roughly 3 solar masses of energy went off in the form of gravitational waves. And we were to detect it later. The distance away in light years was 1.2 billion light years away. And if we translate to what that meant on the Earth's surface, we were just evolving from single cell to multi-level cell life on Earth. And so by the time the signal got to us, we became us and were able to detect it. So progress now, and this is where we start. There's no AI or machine learning in what I just showed you. So, but we've been step by step putting in the modern tools which help us. Maybe the most important one is to make this decision quickly of where something came from, to enable us to do what we call multi-messenger astronomy. And that is that we measure in 3 different places on the Earth and try to decide quickly and reliably that we see a gravitational wave signal and alert the astronomical community. Again, in the end, we use statistical techniques because we want enough reliability so that the astronomers don't lose faith in us when we say, oops, we were wrong, when they turn their instruments. But we use modern AI and machine learning techniques to actually do the calculations themselves.
Quick question. How quickly do they need to turn to see if they'll miss the...
We try to, I think I may have it on the next slide. If I don't, I'll say. We decide in a few minutes. It takes maybe an hour to turn things. The signals, depending on the frequency, can go weeks. So it depends what it is. But we want to decide in a few seconds. But then we have to have an ability to say, oops, we were wrong, and not do it very often, maybe a half hour later, so that they haven't done much more than mobilize, but haven't invested a lot in turning their telescopes in some direction. This is the first and maybe most important event that we've seen in multi-messenger astronomy. That is the collision of 2 neutron stars, and it's shown over on the left here. So you see on the left 3 plots or 4 plots. The bottom one is the gravitational waves. It's a time frequency plot, and you see the little line that goes on that plot here is the gravitational wave signal as seen in LIGO, and it was very clean in LIGO. I'm not going to go through those details. If we project that up in time, these are satellites that we're looking at high-energy gamma rays. So if you look at the top one or the second one, within about 1.5 or 2 seconds, they saw a signal as well. And that was what gave us the confidence to alert the astronomical community. A side remark is that we expect that when gravitational waves are emitted, which has to do with a gravitational interaction, that's going to be slightly before any nuclear physics. It would emit photons. That's after it's merged and nuclear physics comes out. So within a couple seconds is kind of reasonable. But we know from analyzing this event that it came from a galaxy that's 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. So within something like 1 part in 10 to the 15, we show just in this little plot here that light and gravitational waves travel at the same speed. So we alerted the whole community. They could tell what galaxy it was in. I'm going to run out of time, so I'm going to go a little faster on this. And then it was looked at in all the frequencies, to answer the question in the front row, out to days when you see the radio waves. And that whole thing was analyzed then, which is the power of multi-messenger astronomy, to understand what happens when two neutron stars collide. And it fits a model that's in the literature called a kilonova. Everybody's heard of a supernova. That's when a star collapses by its own, burns up its fuel and collapses. This is a kilonova. And a kilonova has an interesting effect. So the kilonova is what we saw. Once we saw that, you can calculate, actually, what happens in the kilonova itself, and it solves a problem, which is the way science works. It has nothing to do with physics, a geology problem that I remember from the time I was a graduate student, which is that the universe is made out of hydrogen and helium dominantly. Otherwise, they're stars, and the stars have a few heavier elements, and they burn by the fusion process. So we make heavier elements by the fusion process in stars, but the fusion process only works up to iron. So we can't explain by that simple argument where our favorite metals got into the earth, like gold and platinum that we love so much. And so that argument, which is what I learned as a student of where heavy elements came from, is probably wrong. And the right argument is that earlier times, neutron stars collided and made these heavy elements, which is an illustration of the fact that sometimes the science you get can move a long ways from what you're doing if you keep your eyes open. So that's the fact that in this one supernova model, it made 100 Earth masses of gold. So that's the argument. We now use, to make the instrument even more sensitive, modern techniques called squeeze light, which is a quantum effect, which I'm not going to talk about, and the sensitivity gets better and better to do that. Deep in the modeling of how we do something like squeeze light, we use AI techniques. With that, even though it was a big success to be able to see gravitational waves, the plot on the left shows how much we've been able to improve since then by doing more modern techniques of interferometry. So the slopes, this is the number of events versus time. We now have something approaching 300. And the slope change is what's listed there as 01, 02, 03. We basically take observing run 1, observing run 2, observing run 3. In between, we improve things and have made it a better instrument, and the slope gets higher. A comparison, so one is that we get more events. The second is that they're much cleaner. I've picked here a recent event, this less than a year old, on the bottom, which has more or less the same parameters, are close to the first event that we ever saw. But you see the first event has a lot of noise going around on it, and this one very little noise. That enables us to have much cleaner events. And in this case, we were able to test a fundamental theorem that we weren't able to by Hawking, that we weren't able to in the earlier data. So now we have hundreds of events, and we're able to compare with various astronomical models, and that'll only get better and better. And we have events that we're still working on. On the upper left is the tests we're able to do on general relativity. And so far, we've seen no violations of general relativity and are able to set a limit on whether there's a thing called a graviton that might go along with it at a very small level, 10 to the minus 23. On the bottom left is the fact that, as you might expect in a few hundred events, we have some that we can't really explain. I'll tell you what that is. And that is they may be measurement errors, they may be real. At this point, we just take it as an observation. We know that there's objects, fundamental objects in the sky called neutron stars that are 1.4 times the mass of the Earth. and it has a fairly small sigma. Heavier than that, the only object that exists that we know about are black holes. And the black hole can only be a black hole if it's heavier than some limit, which people have calculated as typically about 6 solar masses. So between 1.4 solar masses and 6 solar masses, there shouldn't be anything, but we have several events. So we're not sure yet whether that means anything, but that's what we have. Now, in terms of AI and machine learning, we're using it extensively to help figure out how to make a better detector. This is incremental. As I say, we're using it for the optical design. We're using it for making the signal processing optimized, and it's a central tool in kind of all the engineering designs as well. We have a concept now for a next generation detector. In the present environment, it's not being proposed to be funded because funding agencies are kind of crippled in the present situation. One last thing, which is for me maybe the heart of the problem, is that we would like, ever since I was a student, to somehow figure out how the universe began and how it evolved at early times. We don't have good tools to do that. The best tool that we have is what's called the cosmic microwave background. And there we look at the shape of the cosmic microwave background and we get kind of a photograph, if you want, of what the universe was like 380,000 years after the Big Bang. Earlier than that, we had what happened at the very beginning as a puzzle. The fact that it seemed to have grown very, very quickly, something people have heard the word inflation maybe, and we can't probe that. There's two possible ways we could do that. And one is with neutrinos. There are many, many neutrinos that were made in the very early stages of the Big Bang. But the problem is that those neutrinos have thermalized, and they're so low in energy that at present we don't have a viable technique to detect them. Maybe someday, but not now. The best possible way to look at the earliest stage is gravitational waves, which would go back to the very earliest time in the creation of the universe. And we don't yet know how to do that. It means detecting gravitational waves that are much lower frequency than the ones that we've detected. So instead, the way we presently have our best picture of the early universe is by combining all the things that you kind of hear about, and that's in this plot here. If you look at the left-hand side where it says hadron collision, that's the part of a density versus temperature plot characterizing the early universe that's covered by the Large Hadron Collider at CERN. The next one, which says heavy ion collisions, is what's being done at Brookhaven, where they collide heavy ions to do nuclear physics, but basically cover this part of the plot. And then if you move down to the further right-hand side, it's the part that's covered by studying neutron star collisions in gravitational waves. So in an indirect way, we're developing a pretty good picture of what the early universe might be, but directly that remains for the future. And that's all I have today. Thanks.